think. Okay, so this will be your last tutorial for 297. And this tutorial will be about M4 and parallel programming, multi-threading. So as you should already be learning from the lectures, milestone 4, you will be given a bunch of depots, a few number of pickups, and a number of drop-offs. And you should be able to find the fastest delivery route that starts and ends at the same depot. It picks up everything and it drops off everything in the right order. How do we do it? The first step is to estimate the travel time between all of the locations. And second step, find a good delivery ordering that is good because it requires less travel time, and return the final tour. And all of these can be done by a number of ways. It can be really slow, but accurate using brute force. Like you can run Dijkstra on everything, and then you can just put them together in any order. But everything has to be done in less than 50 seconds, which is why we will need algorithms. For the first step, estimating travel times. And you should be eventually estimating them and putting them into a matrix where you can find the path, the travel times and the path really quickly by just looking into this matrix using that from and to intersection IDs. Option 1, estimate by distance. For each of the interested intersections, you can just compute their distance in space. This is fast because it's just one single math calculation, but inaccurate because it doesn't take into account of any path information. Second option, use the exact path. You can compute them by Dijkstra or A star from milestone 3. This is accurate, but it's going to be slow because you have to round it for everything. There's this example code of running A star to fill out that matrix that I just showed you. So for all of the sources from the interested intersections, like your depots, your pickups, and drop-offs. For all of the destinations, you find out the path from the source and destination using A star. Let's say we have K depot, pickup, drop-off intersections and V total intersections. What is the complexity of this? In class? How do we compute the complexity of this nested for loop and a call to A star? What's N? We have K and V. K squared to go through the nested for loop, and there's also a time to compute the path, right, from A star. What's the complexity of A star? It's V log V. So the complexity is k² times v log b. But on large test cases, when k is large, this k² can destroy your time. And it will limit time for your ordering optimization, which is your second step. So now, because we should already know that Dijkstra can run once, and it can find the path to all of the destinations for one source. So instead of A star, we can just run Dijkstra multi-target on all of the sources. This is significantly faster. And what is the complexity in this case? KV log B. So KV log B compared to k² V log B. And this will be the best you can get from the algorithms. But what if we want even more speed? This is where parallel programming comes in. So this is just a picture to motivate using parallel programming. This line that grows and grows is the number of transistors on chip each year. And by Moore's law, it will grow and grow. However, the single-threaded performance is bottlenecked by some extent around 2010. And the other ones are the hardware frequency, power. These are all saturating, like they are not getting better. And power is also not getting more and more. But we are getting more number of cores. And that is what we can use to get more performance instead of single-threaded performance. So now we have multi-core processors instead of single-core processor. And all of the cores share the same memory. Each core can execute its own instructions. And the 4 cores can execute different instructions at the same time. All of them share a common memory space. The applications you've been writing are all single core. So it's just one core communicating with the shared memory. Most applications use one thread, and you have been taught to write single-threaded applications. And because it's just single-threaded, it's only one core talking to the shared memory. The other cores are idle, so you don't need to worry about sharing the memory. The memory is all yours. However, if you want to start with multiple threads, you will need to worry about sharing the memory. You don't want to mess with the memory that the other core thinks you're not messing with. So yeah, multiple threads could modify the same variable. And if both of cores are writing to the same place at the same time, no one will know which one will win. So your memory will get a corruption in that case. This is EC243 stuff. So your CPU or your core for a single-threaded program, it has a program counter, the PC. It has a stack pointer that points to a place in the stack. Your program counter will always point to somewhere in your instructions, which is your code compiled into machine language. And this is always stored in the first few chunks of memory. In the second chunk, you have the global variables in your code. In the next chunk, you have heap variables that are dynamically allocated and scrolling up. Your stack starts from the end and it rolls down. This is all for a single-threaded program. If you add on one more thread, you will have 2 cores. Each core will have its own program counter and its own stack pointer. Program counter is always pointing to somewhere in the instructions, and the instructions in memory is shared between all of the cores because you're only reading from the instructions, you're never writing to the instructions when the program is executing. Your stack pointers are pointing to different places. Each core will have its own stack or local variables. But your global variables and heap variables are all shared. And this is just repeating. Each thread has its own program counter. It can be executing a different function, but it's almost always executing a different instruction. Each thread has its own stack, which means it has its own copy of local variables. Each thread sees the same global variables and dynamically allocated memories. And any thread with a pointer to it can access, meaning it can read and write. Some implications: threads can communicate through memory. If the threads are designed properly to communicate, then when one of the threads modifies something in the memory, the other threads should know. And the other threads can get updated by just reading in the memory. Global variables dynamically allocate memory through pointers can both be used for the communication. But you must be careful that they don't conflict in reads and writes to the same memory. If the 2 threads update the same global variable at the same time, you won't be clear which update will win, and it will most definitely mess up with 1 or 2 of the threads. You can have more threads than CPUs. So for each CPU, if you have more threads, the threads will fight over the CPU resource. And that fight will happen inside the operating system and the hardware microarchitectures that the programmer will never be caring about. But you should be beware of that, and that will be why having more threads doesn't speed things up. It could slow things down. And after finishing with the theory, let's go into the coding. At program start, you're always in your main function, and the program will create a main thread. If you need to make more, you have 2 options. The first option is to use OpenMP, which is adding this line before your for loop. OpenMP is a compiler derivative, and it's higher level code, which means that you don't need to code everything for yourself. The compiler will do everything for it. And this will happen during the compile process, and if your compiler doesn't support OpenMP, it will just run serially. It won't break your code or anything. For the second option, you can use C++11 threads library, which is just using the include thread library and create a thread like this. Thread, the name of thread, and the function to run on this thread. And after everything's done, call join. We'll join the two threads together. And we can continue with your single-threaded program. And then I believe some of you are already doing this, like loading the streets database and the OSM database together at the same time using threads. Let's look into the first option of OpenMP. So you have a for loop that does 100 iterations. Adding on this pragma OMP parallel for will then split. If you have a 4-thread computer, it will split into 4 threads, where the first thread will do the first 25, second thread will do the next 25, and so on. It will split them into continuous chunks of iterations. And as a side note, anyone knows why they are continuous? Why do we not like put 0 on thread 1, 1 on thread 2, 2 on thread 3? Not really. It has some speed optimizations on this. So this decision was made because the your core has a cache. Each core will have its own cache. And the cache will fetch memory from your shared memory. And when each time you fetch, you're fetching a page of memory. And the page of memory is always continuous inside the memory. Usually, if you're in a for loop, you're most likely dealing with something like arrays. And continuous data in arrays are stored by each other. So when the cache fetches a page of memory, it's most likely continuous in one array. So if you split those up, then both of them will fetch the same thing. And this one will look at the first one, this one will look at the second one, this one at the third one, at the fourth one, and it will need to fetch another one. But if you do it like this, both of them can then just fetch different ones. And this one can just do 1, 2, 3, 4. And this one will do 1, 2, 3, 4. So it saves time fetching the memories. In most cases. You can also try by just writing code that will distribute like the memories across, and you'll see a significant slowdown compared to this. And after the for loop, just all of the threads will be joined and we can continue the program execution. Next, I'll show you an example of this. So we have this program. We have a vector length of 1000. We're making 3 vectors with 1000. And we're initializing the vectors A and B. Start the timer and we'll just do a for loop, and this for loop will first get the number of threads and it will do some operations on A and B and store into C. And this is just to make sure the compiler doesn't over-optimize out the for loop. We want to see something in the for loop. And we will then output the time and number of threads. So if you want to double check the number of threads created by OpenMP, you can just use this function and output like this. So to use OpenMP, you'll have to include this header. Include omp.h. Okay. So currently, OpenMP is not. So this line is commented out, so we shouldn't be multi-threading this program. Let's test. Remember this time and the number of threads. So this is a single threaded program and the time is 33.68 microseconds. Now let's enable multi-threading and see. Now we have 16 threads, but the time is actually longer. Any ideas why? Even if we have 16 threads. Maybe this line is taking the time. Let's comment it out and see. Nope. So why is multi-threading getting that longer? Getting the time longer. So multi-threading with 16 threads actually made it slower. Too many threads? Not in this case. Let's increase the number of data. And still use multi-threading. Remember this time and let's disable multi-threading. See, if you have enough operations, if you have enough work, multi-threading will be faster. And previously it was slower because making the thread also take time. So in small enough programs, it's better to just use single-threaded because making the threads might take more time. If you have enough work to be parallelized, then use multi-threading. Get back. So these are the speed ups that we measured with the same program. So with program sizes like 1,000 or 100,000, the speed ups are actually slower. But if we get more, the speed up will eventually converge to something like 7.6 to around 8. And why is that around 8? Remember we had 16 threads. Let's look at the machine itself. LS CPU will tell you the information about your CPU. So you have the architecture, you have your optimal byte order, address sizes. CPUs is number of CPUs, 16. Which is why it's making 16 threads. Cores per socket is 8, threads per core is 2, which means that this computer has 8 cores, and each core can run 2 threads, which makes it 16. And in this case, because we only have 8 cores, the speed up will converge to 8. So the 2 threads per core is not helping with anything because each core has its own resource, and if that resource is exhausted by one of the threads, it will be limited by the number of cores instead of the number of threads. Okay. Everything makes sense. Let's move on to the second program that we are going to talk about. So in this program, we have A and B both having 100 elements. A has 50, B has 2. And in the first for loop, we are adding them together and storing into A. So A will become 52. In the second for loop, we are outputting AI. How to make this multi-threaded? First, include OMP. And then before each for loop, we add the Pragma OMP parallel for. And this will just multi-thread this for loop, join it, and multi-thread the second for loop. These variables will be shared by all threads because they are declared before this for loop, this compiler flag. But the local variables like I that are declared after this flag are local variables that are just local to each thread. The I is not shared. What will be the program output then? Any guesses? Let's take that question and at first do a typing speed contest. So I brought a separate keyboard and there's a keyboard on my computer. So I want the two of you to come and do this contest. So I'll open up two notepads. Open up another one. So the first one to type out this line, open. So yeah, you can decide which one wants to take the that's taking the laptop takes the mouse.
Oh, okay. Do we just start? Or
Yeah, you can type on this one, you can type on this one.
oh, okay.
Yeah.
So like, oh, okay. Oh, I'm sorry.
Yeah.
Okay. Ready? Oh. Oh. Oh, oh yeah, it's going into the same notepad.
Yeah.
Oh. Oh wait, how does
And because you have the mouse, so
yeah.
the mouse.
Oh, I see. Okay. Wait. I can't wait. Oh my god. Wait.
Like in the example, they would both print out like separate, right?
Oh my god, it's
Oh, I think I'm talking
you are. There.
about.
Yeah, you can take chocolate bars before you leave. Yeah, so you should get the idea. And this is also what happens with this program. So different threads are fighting over the same resource. Thank you. And anyone can win. So let's go to the code and let's try with the code. So what the code does, it's the same code. We have the two for loops and the two open empty flags. I'll make and I'll print. So you'll see that the printing is not as what we expected. It looks something like this, right? So how do we fix it then? This is because the printing. So the C out, multiple threads are fighting for the same C out. So they're sending things simultaneously without any ordering. What we can do is, let me first time this so we get the time of this executing. 0.169. What we can do is that we can define this section to be critical. So all of the threads, if one thread is executing this, the other threads need to wait for that one to finish before doing the same thing. And this is done by setting pragma OMP critical. And this will set this entire bracket, everything inside this bracket to be critical. Make and time. Do we have the right outputs? Even if they are not in the right order, but that's fine because we are multi-threading it. Okay. And I was supposed to show you that the speed is higher, but it's not in this case. So making things critical will slow it down. But in this case, it's not. Okay. Let me get back. So as I just showed you, setting this stuff critical will help. Because making everything multi-threaded can run different loop iterations on different cores in parallel, but it does not check if that is safe or correct. So if you want to ensure correctness, set the things that you want to get only one thread at a time to execute into critical blocks. And making it critical is like adding a lock on it so that only one thread can grab that lock. And when it finishes, it releases that lock and the lock can be grabbed by another thread. So this will make the program slower. Yeah, making everything critical means that you are doing serial programming again. You're not benefiting anything from multi-threading. Everything makes sense to this one. Okay. Next, let's get back to our milestone 4. So these are the measured times measured by us using the 4 options that we just discussed. The first one is iterative A star without any multi-destination Dijkstra or without any parallelization. We're using that as the baseline. Next, we parallelize this A star and we can see that it converges to something like 7.6x because we have an 8-core CPU. And then we use the multi-target Dijkstra, and we can see that it's already a 33x speed up compared to the baseline without parallelizing. Adding on parallelization means that it's multiplied by another 8 times, making it 250x. And what we want to tell you is that it's the best to first tune the algorithms to the most extent that you can do before parallelizing. Because parallelizing doesn't give you that much gain compared to just getting a better algorithm. Just do it after you get the best algorithm. Now, here is the code on the multi-destination Dijkstra. So you have your priority queue, you have your vector of nodes, you have your vector of intersections, key intersections that contains all of the depots, the pickups, and drop-offs. First, for loop, it goes through all of the key intersections and it finds path from the source to everything else by calling this find path function. And this find path function is just a single run of Dijkstra. How to make this parallel? Before the for loop, we add in this compile flag to make this a parallel for. But will this work? Let's consider the variables and what it's doing. Will this work? Any thoughts? Think in terms of shared memory. Yeah. Yeah, so the force is local. The path is global, but we're not talking about that at this point. Think about find paths. You have multiple threads executing find paths. And these variables are global, which means that they are shared. Is that a problem? Yes. So the largest problem with multi-threading is that we don't want multiple threads to write to the same location. So if you are pushing into a global variable at the same time, it can cause problems. Which is why, yeah, we have the shared globals and each thread can be modifying the shared global at the same time. Which is why we want to move them into the find paths function to make them private, to make them local. And this is called privatized. So we're privatizing the global variables. So now if they are doing this, it's safe because they're just modifying their own code. What about the T intersections, this variable? Should we privatize that as well? No, because we're just reading from it. We're never writing to it. If we write this code like this, if we have the priority queue and the nodes as local variables inside a function, and we're passing by reference of them into the find paths, is it okay? Is it okay? Is it not modifying the original ones? Or passing by reference? Yeah, everything declared before the parallel 4 are shared across all of the threads, and especially you are passing in by reference, so all the threads can modify them. So we still want to privatize those as well. Go to the demo. I do it on the golden solution. Of milestone 4. And because I don't want to spoil everything for you, I'll just be looking at this function. Find all paths. And this is the for loop to be parallelized using OpenMP parallel 4. Let's test it. Energy is so slow today. Let me switch to another one. Hey. And I'm going to run the public Easy Toronto one. Okay, so the travel period took 0.7155 seconds. Let's disable multi-threading and see if it affects the runtime. So comment out this line. Go to terminal, make. And test. Remember we previously had 0.7 seconds. .88. See the difference. Okay. And next, let me turn this back on. Remember the two global variables that we privatized into local variables? I'll be showing you that that's actually the case. So we have these two variables that were global before and we privatized them. So now I want to make them back global again. So I'll define this. And this one will then declare this one as global, and it will turn off the local declaration of this variable. And let's see what happens with multi-threading enabled. Do a make. And run the test. So we failed the test. And let's look back into the messages. It says double free or corruption. Means that we have a memory corruption somewhere. And memory corruptions are caused by threads writing to the same thing and messing up with each other. So if a memory is modified, but the other thread doesn't know, that the other thread will see a memory corruption. How do we debug this? Oh, yeah. First thing, I want to show you that this is actually caused by multi-threading, not by what I just did. So I just commented out this line. So we disabled multi-threading. And run tester again. And we pass the test. So it's actually because of multi-threading. If we want to debug this, let's run a debug tester to get the tester file. And in the make file, use the configuration unit test debug, build target test lib street map, launch target test lib street map, build in debug mode. And start the debugger. Wait until it finishes. Wait until it crashes. So it crashed. thread 15. So if you look at the call stack, this will have the list of all of the threads that are active at this point. And it says thread 15 raised the crashing signal, and let's find out in the call stack, the last thing that we can recognize, which is here. We are trying to resize all nodes. And most likely, if you look at some other thread, you'll be able to see another resize. Or something like that. Something's doing something to all nodes, which is the global variable. And the other thread is trying to do something similar to it. It's trying to write to it, and it causes a memory corruption. Okay, makes sense? So that's all nodes. Let's go to the top of m3.cpp and let's private has all nodes, and we want to see the priority queue as the global variable. And let's see what happens. Make and run tester. Okay. Double free or corruption. To make sure, again, let's disable multi-threading and see if this goes away. Run tester. Passed. So it is because of multi-threading. Let's enable multi-threading again and run the debugger again. And it crashed. in thread 11. Constant exception, this one. And let's see. Here, it's trying to push into the priority queue. And if you look at any other thread and not this one. Yeah, you'll probably see another one that's also pushing into a priority queue. Okay. So that's just one way of debugging multi-threading problems. And in this case, we got something like crashed test. And this is the first time I got it with the priority queue issue. Usually the program can get into an infinite loop where like different threads are trying to resize and they're waiting on each other and they are getting into an infinite loop and we're getting an empty path. So yeah. Back. Yeah, so key takeaways are just, if you have something with multi-threading, first thing, disable multi-threading and see if the problem goes away. If it goes away, then probably there's some global variable that's having the issue. And then you can go into the debugger and you can see either where it crashed or if it goes into some infinite loop, you can just close the debugger and examine the callback. And most likely, if more than one thread or two threads are working on the same global variable, then most likely that's the issue. And next, remember the path matrix that we were talking about. So this is the matrix where we want to store the result from the multi-destination Dijkstra. And we call it paths. We make it a vector of vectors of paths. So this is a matrix to the array. And we're pushing back from the result from find paths into the paths matrix. And what it looks like will be, for the paths, you have a vector in this dimension, and each of the vectors will have a vector in this dimension, and you can then use the intersection IDs to access each path that you're interested in. Then if we have this code, is it okay with multi-threading? Are there problems? I don't know why. So in this case, the only global variable is the path, right? And you're doing pushback into the path. Do you know the order? Well, if we are serial, then we almost always know that it goes from 0 to whatever. And it's in ascending order, continuous ascending order. But if we are multi-threading the for loop, do we know the order of the thread? And we want to access the element using index, using street index. So the pushback won't work because the pushback order will be arbitrary. So your data will be misordered. And if multiple threads are trying to push back together, you can get problems with reallocation or copying, resulting in loss of data and memory corruption, which happens with the vector resizing and the priority queue that we just saw. So, no. How to fix it? We want to first resize the paths to have the size that we want. And we have a fixed index to save the path into, so that different threads will not save to the same address. So we have the we have the I row, which is local, private to each of the thread. And we are saving the paths into paths I row, so that different threads are not interfering with each other. They're saving to the same matrix, but different positions in the matrix. Does this make sense? Any questions? So yeah, this is just summarizing what I just said. Debugging parallel programs, first disable parallelism. If the program disappears, then it's probably a race condition where multiple threads are writing or reading a shared variable. Usually reading won't cause a problem, but if some threads assumes that no threads are writing to it, but some thread is writing to it, then that's a problem. That's the only problem with reading. If multiple threads are writing, that is the largest problem. You can run it in debugger and you can see all of the threads. I think this is how you can see it from NetBeans. And I just showed you how to see it from VS Code. And you can examine the call stack for each. And likely, if multiple threads have are doing something to a shared variable at the same time, it's likely a race condition. Fixing race conditions, the first option is to privatize the variable by moving it into a local variable of each thread. Or if this is not possible, you have to keep it shared. You'll need to use the OMP critical to force that section such that only one thread can read or write at the time. This is not as good a solution because it costs for performance. So only use it when you need to. Only use it when the variable is not privatizable. So Amdahl's law. Amdahl's law states that the maximum speedup you can get from parallelizing a portion of your code is this equation. Suppose we have n cores and we have the f as a fraction of your work that is parallelizable, that you're parallelizing, the speed up will never exceed the result from this computation. So if your, say, your portion of parallelizable work is like half of your entire program, then your speed up will never exceed 2x. If you have 95% of your program that's parallelizable, then you can exceed something like 20x for more and more processors. So increasing the number of processors will stop to work at some point. This is what this graph is telling you. Okay. Is this clear? Is this slide clear? This is a really useful equation to use when you want to speed up something. And you'll know to which extent you can continuously speed up using parallelization. So takeaways. First, always improve your algorithms before attempting to parallelize, because improve your algorithm usually is a bigger reward. Use the OpenMT pragmas because they are flexible and higher level, and it's easier to use. Avoid modifying shared state to minimize bugs with modifying shared variables, and privatize variables so each thread has a copy. Parallelize large chunks of work instead of just some small work, because your program making threads can cause overheads. Parallelization is hard. Experts will get it wrong, and there are research problems that are just working on how do we parallelize this problem, this problem. How do we parallelize that problem? So it's hard. And for your M4, our suggestions is just first get something simple working using the simplest algorithm you can get, and then try, because we have given you already the multi-destination Dijkstra. You should be able to use that for travel time estimation. Then for your ordering and returning a legal solution, try using the simplest one first, and then use better ones. And when you cannot optimize further, then parallelize. Add parallelization only when everything is working well, and if you want to make it better. Yeah. And yeah, that's it for today's tutorial and your last tutorial. Thank you for coming.